Hello, my name is William, and for my self-reflection, I want to discuss why this paper is such a significant contribution to the software engineering discipline. In my opinion, the true usefulness of this work lies in how it transforms program slicing from a reactive maintenance tool into a proactive development tool. Before this, slicing was mostly used to debug complete applications after they crashed. But by introducing the ability to slice incomplete systems like isolated classes, this research allows developers to verify the code modularly while they are still writing it. This aligns perfectly with modern component based software engineering. So, to analyze the research objectives, I focused heavily on the introduction here on page 1. Um, I specifically looked at for where the authors define the gap in existing methods, and I found the key sentence here, which says, "Thus, an inefficient graph representation for object-oriented software should consist of a class representation that can be reused in the construction of other classes and applications." And it further goes into saying that an efficient graph representation for a derived class should facilitate the reuse of analysis information and also, fast forward a bit, reuse analysis information computed for base classes and only compute information that is defined in the derived class. So using these information, we can tell that we can reuse the analyzed class when the class is inherited again. So that significantly reduces computational costs for program slicing and analysis. So, and this sentence was very crucial for my analysis as a whole because it revealed that their objective wasn't just to make slicing work for C++, but to also make it efficient through incrementalism. This distinction helped me understand that their primary innovation was the class dependence graph as a reusable asset, which they later describe in their representing base classes section of their paper. Now, when I was analyzing the scope, I initially struggled to visualize how they handled polymorphism. So I analyzed when I got to figure 5 down here. This is where things started to become clear because the diagram clarified the technical depth of their scope. If you're looking, for example, P1, this is the polymorphic choice vertex that has to do with the line C38. It shows you physically how the graph connects one call to multiple destinations, shown by the different arrows connecting to two different nodes, right here and here. So this visualization helps understand why this is strictly limited to statically typed languages and why this wouldn't work for dynamically typed languages. If this was statically typed, if this was a dynamically typed, there could potentially be many more different vertexes, many more nodes, many more vertices, many more edges that these will have to go and connect to, which would create a uselessly large graph. So for EPTR, E pointer calling the go method, because the go method could be either from the alarm elevator class or the straight up the elevator class. And because of that, we can see at a runtime, EPTR can be either alarm elevator or the elevator already. So the P1 vertex allows to trace what happens, whether it's, for example, if it goes to the left side, it could be the alarm elevator's go method executing and knowing what happens after that, or calling the elevator's go method, which will go to the right side of this and will know what happens if it's calling the go method in the elevator class instead of the alarm elevator class. With this, I think this made me realize that it would be impossible, right, if there were too many connections in a dynamically typed language. So that inference was how I determined the strict boundary of their scope. Regarding the challenges that I've encountered, I think one of the hardest part was distinguishing between the system dependence graph and the class dependence graph, because a lot of the time you would say CIDG throughout the entire paper, but the output is actually an SDG. So CIDG being a class dependence graph and SDG being the system dependence graph. So at first, I read when I read it, the terms seemed like they were interchangeable, which didn't make sense because SDG was something that already exists according to what they said at the beginning of the paper. So I had to reread the section 3 multiple times until I could finally grasp that the CIDG is actually a modular component, not an entirely new graph. And CIDG that is a modular component that can be used to create an SDG, which is the result linking all the components together. So finally, I would like to say that my opinion on the work is that its greatest strength is the reuse mechanism. The idea that you don't have to reanalyze a library every time you use it is a massive efficiency gain. However, I believe the limitation lies in the conservative nature of their static analysis, because they map every possible polymorphic path to ensure soundness. And I suspect for very large complex inheritance hierarchies, these graphs could become massive, potentially impacting performance in a way that the paper didn't fully address.